Today we're going to have a look at an example question from the Floyd textbook. It's example 24 from page 271 out of the 9th edition, which we use. Not too dissimilar, this question, from the previous question we did with the toggle switches in it, in as much as we've got after that question was redrawn anyway, we had a central voltage source, and then we had some resistance to the left-hand side of that and some resistance to the right-hand side of that, and using some very basic circuit analysis technique, that allowed us then to solve one side of the circuit independently to the other side, because we've basically got a voltage source, parallel resistance on this side, and a parallel resistance on this side. So they are in fact two completely discrete circuits, and unless we needed to work out the current that was flowing at this point here, we can consider those two circuits completely independent of each other. And this question gave us the fact that we had two voltmeters, one here with 3.67 volts on it and one on this side with 6.65 volts on it. And the question goes on to say, are there any open circuits or shorts in this question? So very, very typical of what you might see in an examination, and there would be other questions asked about this circuit as well. Hint, hint, maybe what would the total current be there with the faulty circuit and with the good circuit perhaps. But today let's have a bit of a think about this circuit, and this is where I need you to think about something which I learned many, many years ago from a book by Malvino called Circuit Approximations. And basically it's a case of being able to work things like this circuit out without the use of a calculator. Just looking at the basic values that you have in front of you and working with those values and rounding things off makes it very quick in an examination for one. And also, if you do the circuit approximations first, then when you do want to take out your toy, your calculator, and press buttons on it, if it doesn't match up with the approximation, you know that you've probably made an input mistake on your toy. So always think about what ballpark you should be in with a question like this. Now, for example, here in this left-hand side, this left branch of the circuit, I've got 3.3K, 15K, that's about 18K, plus 3K, that's about 21K. These all add together to be about 21K, and then we know that we've got 24 volt supply, so 24 divided by 21, that's going to be about 1.1 volt. About 1.1 volt per k ohm, and then we've got around about 3.3k there, so 3.3 times 1.1, that's going to be around about 3.4, 3.5 volts, something like that. So I'd say this side of the circuit is looking pretty good. Another way that you could have looked at that, you could have said that the 3k was around about 1/7 of the total voltage divider there, and then therefore 1/7 of the 24 volts would be around about 3.5 volts. You could do that as well. So whichever way you come into it, you've got about 3.5 volts. That should be there. So I'm pretty happy with that. I'm going to give that a tick. On the other side of the circuit, 6.65 volts. We can do some simplification here as well. 15k, 2k, got about 17k from those two in series. And then I've got, we haven't got a value on that. That should have been 10k. So we end up with 17k in parallel with the 10K. 17K in parallel with 10K. Well, if we had 10K in parallel with 10K, we'd have 5K. And if we had 17K, let's say 20K and 20K together, we're going to have 10K. So the value is going to be somewhere between 5K and 10K. I'm going to call it around about 7K ohms. Look, I could be wrong. It's just an approximation. It's a guesstimate at this stage, but I don't think it's too far off the mark. So 7K in series with 4K7, that's going to be the 7K plus, let's call it 5K. That's going to be 12K. And then, just like we did on the other side of the circuit, we had 24 volts and we've got 12K. So we can say now then, with our approximated values, we can say that we've got around about 2 volts per K ohm in the circuit. So 2 volts per K. I know that downstream of that 4K7 then, I had 7K. 2 times 7 equals 14 volts. This is where things go a little bit stray. We've only got 6.65 volts shown here. Circuit analysis says that we should have 14 volts, even with approximation. And the approximation wouldn't be out by that much. So therefore, there's certainly something wrong with the circuit on this side. What can it be? Well, that's where we have to think, has something gone open? Has something gone short? If the 10K resistor went open, we'd have 17K in series with 4K7. In fact, that would go closer to giving us the right voltage. But the 10K obviously hasn't gone open. Has something gone short? Well, if one of these resistors went short, if the 15K resistor went short, I'd have 2K in parallel with 10K. That's going to be about 1.8K. I'm going to have an even lower voltage than that. So let's go to the drawing board then and have a look at that circuit and just do some sums on it. And we're going to have to do trial and error here and work out exactly what it is. All right, so you can see in this circuit then we have 3.3K with 3.3K, 6.6K with 15K, that is then 21.6K, 21.6K, and then we've got 3.3K, which the voltage is taken across here, 3.3K, and then if we run the maths on the calculator with that, just let me do that, 3.3, no need to put K because it's all in K, divided by 21.6, 0.152, we need to add something to our equation there to get the final voltage, and that's going to be, of course, times 24 volts, isn't it? 24 volts. 24 volts, so times 24 times 24 equals 3.66 volts. Equals 3.66 volts. So, like we said in the main part of the video, this gets the tick. There's nothing wrong with that side of the circuit. This side of the circuit, though, we worked out in the previous part of the video that we had way too little volts. I think we should have had about 14 volts there, and instead we've only got 6.65. So we've got the question, something might be short circuit or something might be open circuit. Well, very quickly, let's rule some things out here. Could the 10K resistor be a short circuit? Could that be a short circuit from there to there, The answer is, of course, no. And why not? Because if that was short circuit, we would have then 0 volts there, not 6.65. So I think we can safely eliminate that. What about if the 15K resistor went short circuit though? Let's get that first short circuit off there. Take that away. If the 15K resistor then had a short circuit across him, we'd have 2.2K in parallel 10K, 2.2 in parallel with 10. I think we said before that'd be about, I'm only guessing here, 1.8K. If that's 1.8K plus 4.7K, 4.7K, that's going to be 5.7, 6.5K. So it'd be 6.5, and then we'd have the 1.8 over the top of that, and then we'd multiply that by the 24 volts again, 24 volts, and need a bit more space on the bench here. 1.8 over 6.5, 1.8 divided by 6.5 times 24. Again, it's all in k ohms, so we don't have to go any further with that. We can just put whole values in. I actually get 6.6 volts. Well, I work out 6.6 volts there equals 6.6 volts. So in fact, it's very possible then that the 15K resistor could have gone short circuit. That then would balance out the circuit and give us the 6.65 volts that we do have here. Okay, so we've pretty well wrapped up things now. We've proven then beyond a shadow of a doubt. I mean, I did things roughly before, and now you can see I've got a new slide up here, and there's yours truly. And more precisely, I've said here, using the trusty calculator, the 2.2K in parallel with 10K, because we said we had a short circuit across that 15K resistor, so that's no longer in circuit. And that gives me 1803 ohms. I did estimate before about 1.8K. Was pretty close, but we just wanted to be certain because I wanted to see this 6.65 to match the question. So the total resistance then would be 1803 plus 4.7 as a ratio, 1803 divided by the 6503 times the 24 volts to give me 6.655 volts, and that's exactly what we've got across that meter. So just by some simple deduction in the circuit, not too hard then to work out what's gone open circuit or what's gone short circuit, and therefore we've been able to solve the riddle of this particular circuit. It was a troubleshooting question, and there is in fact trouble in the circuit. We have a short circuit. Probably resistors themselves don't go open short circuit, they generally go open circuit. So more often than not, it would be a short circuit on the printed wiring board or something in the wiring which has caused the short across that component. So troubleshooting 101, we've killed it. There's a lot more questions like this one in the Floyd textbook. Make sure that you work your way through these and think about all of these different possibilities. It's a great start to circuit analysis, which is a later subject that we do in the advanced diploma and diploma courses. Okay, I hope that was helpful.